This video is sponsored by Brilliant. Did you know that a refrigerator is actually a very simple machine? If you strip it down to its essential parts, you'll mostly see a loop of copper tubing connected to a compressor. The compressor simply pushes a gas around this loop. Yet somehow, one part of the coil becomes very cold, while another part becomes very hot. How can we make sense of it just by looking at this? We might assume that the gas inside must be some special substance, and that understanding it requires learning a lot of chemistry. But what if I told you that we can understand how to make things cold without worrying about that special gas at all? First, we need to understand an important idea. Making cold is really just removing heat. Making heat is easy. Humans discovered fire thousands of years ago, and since then we've invented countless ways to produce heat. But removing heat, especially removing it beyond what nature would normally allow, is a much more recent discovery. Practical refrigeration has only existed for about the last 200 years. In everyday life, we can remove heat in simple ways. If you blow on a hot cup of tea, the tea cools down, but it will never become colder than the surrounding air. If you place a hot piece of metal into a bucket of water, heat flows from the metal into the water. The metal cools, the water warms, and eventually they both reach a temperature somewhere in between their original temperatures. This behavior follows a basic rule of nature. Heat always flows from a higher temperature to a lower temperature until equilibrium is reached. But a refrigerator seems to do the opposite. It removes heat from the cold interior and releases it into the warmer room outside. So how is that possible? To answer that question, we first need to understand what heat actually is and how it moves from one place to another. All matter is made of atoms and molecules. These tiny particles are constantly moving and vibrating. Heat is simply the energy associated with this motion. When atoms in one object vibrate and collide with atoms in another object, energy is transferred between them. This process is what we call heat transfer. There are three main ways heat can move, and the first is called conduction. Conduction happens when objects touch each other directly. Imagine this metal rod is hotter than this one. The atoms in the hotter rod are vibrating more vigorously than the atoms in the cooler rod. When the two rods are placed together, the fast-moving atoms collide with the slower ones, transferring some of their energy. As these collisions continue, energy spreads through the metal until all the atoms are vibrating at roughly the same level. We can observe this effect with a thermometer. When the vibrating atoms in the metal transfer their energy to the liquid inside the thermometer, the liquid expands. That expansion is what allows us to measure temperature. Another method of heat transfer is called convection. In this case, heat is transferred through a moving medium, such as a gas or a liquid. In a refrigerator, the hot coil at the back releases its heat to the surrounding air through convection. If we look closely at what's happening, the atoms in the hot copper pipe collide with nearby air molecules, transferring energy and warming the air. As the air heats up, it expands and becomes less dense, causing it to rise. When the warm air rises, cooler air flows in to take its place and is heated by the pipe again. This continuous movement of air creates a natural convection current. Inside the refrigerator, convection works a little differently. The warm air generated by the food is pulled by a fan toward the cold evaporator coils. As this warm air passes over the cold pipes, the energetic air molecules collide with the colder metal surface and transfer their energy to it. The cooled air then flows downward to replace the warmer air, and the cycle repeats. Because convection transfers heat through a medium like air, increasing the surface area in contact with that air helps the process happen faster. That's why refrigerator coils often have thin metal fins attached to them, and why the condenser on the back has those zigzag pipes with many small metal rods. These structures greatly increase the surface area touching the air, allowing heat to transfer much more efficiently. The third method is radiation, where heat travels as electromagnetic waves without a medium. We'll explore it later in a video about microwave ovens. Since a refrigerator works with gas, we also need to understand how gases behave in relation to heat. When I say gas, you can simply think of air, since that's the gas we're most familiar with. Unlike solids, which have fixed shapes and rigid boundaries, a gas can expand to fill whatever space is available. Because of this, the heat associated with the motion of its molecules can change depending on the size of the space it occupies. To understand this better, imagine trapping a gas inside a container. The molecules move randomly in all directions, constantly bouncing around and colliding with the walls of the container. The average force exerted by these molecular collisions on the container walls is what we call pressure. Just like heat, pressure is also a result of molecular motion. There are two main ways to increase this molecular motion, in other words, to add heat to the gas. One way is to simply heat the container. As the temperature rises, the molecules move faster, and the pressure increases. The other way is to compress the gas. When the gas is squeezed into a smaller space, the molecules collide with the walls more frequently. These more frequent collisions increase the pressure and also raise the temperature of the gas. This is the same reason your bicycle pump becomes hot when you pump air into a tire. If the temperature of the container becomes higher than the surrounding air, heat will naturally flow from the container to the environment. Now imagine we allow the gas to expand back to its original volume. The molecules now have more space to move around, and since some of their energy was already lost earlier, the gas becomes colder than it was before. In a sense, we have removed heat from the gas. A familiar example of this effect is an aerosol can becoming cold when you spray it. Of course, once the gas becomes colder than the surrounding air, heat will start flowing back into it. But if we separate the compression stage and the expansion stage into different places, we can use this effect to move heat from one location to another through a loop. This is where an expansion valve comes in. Without it, we cannot compress and expand gas at the same time inside a continuous loop. The expansion valve is simply a small restriction. It might be a tiny opening or a narrow coil of tubing that limits how much gas can pass through. Because of this restriction, the compressor can build up high pressure on one side of the valve, while only a small amount of gas is allowed to pass through and expand into a much larger volume on the other side. When this small number of molecules suddenly occupies a larger space, their energy spreads out over greater distances and their motion slows down, making the gas cold. This cold gas can then absorb heat from its surroundings and regain some of its energy. The compressor then draws the gas back in and squeezes it again. By compressing the gas, its molecular motion increases until it becomes hotter than the surrounding air, allowing the heat to be released outside. In effect, the compressor is continuously squeezing heat out of one place and releasing it somewhere else. As this cycle repeats, heat is steadily removed from the cold side and carried to the warm side. This process is known as a heat pump, and a refrigerator is one of the most common examples of it. However, transferring heat simply through molecular vibration is not very efficient, so refrigerators rely on something called a phase change. A good example is water. The same water molecules can exist in three different forms: a solid called ice, a liquid called water, and a gas called steam. When a substance changes from one phase to another, energy is either absorbed or released. For instance, if we heat a pot of water, we would expect its temperature to rise steadily as the molecules vibrate faster and faster. But when the water reaches about 100 degrees Celsius, something interesting happens. The temperature stops increasing, no matter how much additional heat we add. The molecules have essentially reached their maximum vibration at this temperature, the boiling point. So where does the added energy go? Instead of increasing temperature, the energy is used to separate the water molecules so they can escape into the air as steam. Water molecules attract each other somewhat like tiny magnets. We can even observe this attraction at a larger scale when two droplets of water snap together to form a bigger droplet. Just as it takes force to pull two magnets apart, it takes energy to break the attractive bonds between water molecules. The heat energy used to break these bonds is called latent heat. When steam later condenses back into liquid water, that latent heat is released again. It's easy to understand why separating molecules requires energy, but why does putting them back together release energy? The reason is that when molecules come back together, their attractive forces pull them toward each other. As they bind, they collide with significant force, and that energy is transferred to neighboring molecules and eventually released into the surrounding environment as heat. So keep this idea in mind. When a liquid turns into a vapor, it absorbs latent heat, And when the vapor condenses back into a liquid, that latent heat is released again. To see how significant this effect is, consider water. Heating 1 gram of water from 0 degrees Celsius to 100 degrees Celsius requires only about 100 calories of energy. But turning that same water into steam requires about 540 calories. This large amount of energy is the latent heat needed for the phase change. Refrigerators take advantage of this phenomenon by using a special gas called a refrigerant. At room temperature, the refrigerant exists as a gas, but when it is compressed, it can turn into a liquid. This is similar to how the gas in a propane tank is stored as a liquid under pressure. If we compare ordinary air molecules, such as nitrogen and oxygen, with refrigerant molecules like isobutane, we can see an important difference. Oxygen and nitrogen molecules each contain only 2 atoms, while an isobutane molecule is much larger and consists of 4 carbon atoms and 10 hydrogen atoms, making a total of 14 atoms. Since heat is stored in the motion and vibration of molecules, the more ways a molecule can move and vibrate, the more energy it can absorb. Simple molecules like oxygen and nitrogen can move, rotate, and vibrate in only a few ways. But larger molecules like isobutane can twist, bend, and wiggle in many different ways. Because of this, they can absorb much more vibrational energy. They are also heavier than the molecules that make up most of the air. Now that's enough about chemistry. Let's follow the journey of the refrigerant through the refrigeration cycle. A cool, low-pressure refrigerant vapor first enters the compressor. The compressor squeezes the gas, raising its pressure from about 0.6 bar to around 8 bar. As the gas is compressed, its temperature also rises, from roughly -10 degrees Celsius to more than 50 degrees Celsius. This hot, high-pressure refrigerant then flows through the coils on the back of the refrigerator. As it passes through these coils, it loses heat to the surrounding air. Its temperature drops to around 40 to 50 degrees Celsius, but the pressure remains high. Under these conditions, the refrigerant becomes saturated and begins to condense into a liquid. That's why this back coil is called the condenser coil. During this process, when the refrigerant changes from vapor to liquid, it releases its latent heat to the surrounding air. Next, the high-pressure liquid refrigerant, still at about 40 degrees Celsius, passes through a narrow capillary tube. Because the tube is very thin and long, the refrigerant experiences friction and rapid expansion as it flows through it. As a result, the pressure drops sharply from 8 bar down to about 0.6 bar. This sudden drop in pressure causes the refrigerant's temperature to fall dramatically, from about 40 degrees Celsius down to around -25 degrees Celsius. Inside the capillary tube, part of the liquid refrigerant instantly vaporizes. This phase change consumes a large amount of latent heat, which cools the remaining liquid to a very low temperature. When the refrigerant exits the capillary tube, it is now a cold mixture of liquid and vapor. This mixture enters the evaporator coil inside the refrigerator. As the fan pulls warm air from the food compartment across this coil, the refrigerant absorbs that heat. The absorbed heat causes the remaining liquid refrigerant to evaporate, storing the energy as latent heat in the vapor. Finally, this low-pressure refrigerant vapor is drawn back into the compressor, and the entire cycle begins again, continuously moving heat from inside the refrigerator to the room outside. If the refrigeration cycle were allowed to run continuously, it would waste a lot of electricity. To prevent that, the compressor is controlled by a thermostat inside the refrigerator. When the interior becomes cold enough, the thermostat cuts power to the compressor and the fan. I won't be going into the details of the electrical wiring behind these components. That's actually something I've been trying to refresh recently, and I've been using Brilliant for that. It's a learning platform focused on math, physics, and computer science, but instead of watching lectures, you learn by actually solving problems step by step. The courses are designed by people from places like MIT, Harvard, and Stanford, and they guide you through concepts interactively. They have interactive courses on topics like circuits, where instead of just reading about components, you work through how current flows, how different parts behave, and how complete circuits are built step by step. It's a much more hands-on way of understanding how these systems actually work. To learn for free on Brilliant for a full 30 days, go to brilliant.org/Quasar-Ed. Scan the QR code on screen or click on the link in the description. Brilliant's also given our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Inside the thermostat is a small copper bellows connected to a thin tube filled with refrigerant. When the temperature drops, the refrigerant contracts and the bellows shrinks. When the temperature rises, it expands. The movement of this bellow pushes a lever that activates an electrical switch. However, this lever is connected to another lever by a spring, and the tension of this spring can be adjusted using the control knob on the refrigerator. The knob turns a cam that changes how much force is required to trigger the switch. When the cam is set to its highest position, the bellows must expand more to overcome the spring tension, meaning the compressor turns on only when the temperature rises higher. When the cam is set lower, less force is needed, so the compressor turns on at a lower temperature. This is how the thermostat setting controls how cold the refrigerator becomes. Since the evaporator operates at freezing temperatures, there is a risk of ice forming on the coils and fins as moisture from the air freezes onto them. This is a problem because the ice blocks airflow and reduces the surface area needed for efficient heat transfer. To solve this, refrigerators include a defrost heater placed under the evaporator. This is the same resistive heater that is used in electric kettle or toaster. You can learn more about it in my kettle video. The heater melts the accumulated ice periodically, usually about once every 10 hours, and runs for around 15 to 20 minutes. This process is controlled by a defrost timer. In many refrigerators, the timer is a small mechanical device powered by a slow motor that turns at only about 1 to 3 revolutions per minute. Through a series of gears, the motor slowly rotates a cam inside the timer. 3 metal contact strips ride on the surface of this cam. For most of the rotation, these 2 contacts keep the compressor circuit closed, so the refrigerator runs normally. But when the cam reaches a certain position, the contacts switch. The compressor circuit opens and the heater circuit closes. This temporarily stops the compressor and turns on the defrost heater. After the cam moves past that section, the contacts switch back again and the compressor restarts. The cam is connected to the gears through a small internal ratchet, which allows the cam to also be turned manually from the outside to start a defrost cycle if needed. There is also a bimetallic safety switch attached near the evaporator. If the temperature near the coil rises to around 10 to 15 degrees Celsius, this switch opens and cuts power to the heater, even if the defrost timer is still in the defrost mode. The melted water then drains to a small tray at the back of the refrigerator, where it slowly evaporates. You may have also noticed a slider control inside the freezer compartment. Although it may look like it controls the freezing power, it actually works as a small air door that adjusts how much cold air flows into the refrigerator compartment below. When the slider is set toward maximum freezing, it restricts airflow to the lower compartment so more cold air stays in the freezer. Because a refrigerator is constantly moving heat from inside the cabinet to the surrounding room, the way we use and maintain it can greatly affect how efficiently it operates. Placing steaming hot food inside, overpacking the shelves, or leaving the door open for long periods introduces extra heat and moisture that the system must remove, forcing the compressor to run longer and sometimes causing excess frost buildup. It also helps to leave some space around the back or sides of the refrigerator so the condenser coils can release heat properly. That covers most of the important parts of how a refrigerator works. Interestingly, the air conditioner in your home works on exactly the same principle. It simply moves heat from inside your house to the outside. So even though we have found a way to remove heat from one place, we always have to release even more heat somewhere else. In other words, to make one space colder, we end up making the surrounding environment slightly warmer. In a sense, about 200 years ago, humanity discovered yet another way to generate heat. I hope you learned something from this video. If you enjoy this kind of content, please consider supporting the channel by subscribing or supporting me on Patreon. Your support helps me continue creating high-quality educational videos that can benefit people around the world. Thank you for watching, and I'll see you in the next video.